Okay, so we're looking at topic 3.5, initial value problems, question 3b. So they've given us the derivative of a function, and the derivative is 2 sine squared x over cos cubed x plus 1 over cos x. And they want us basically to restore the function. That's the first thing, they'll recover the function. So we're going to have to integrate that to recover it, and then find the area under. It turns out not actually under the restored function. They want us to find the integral. They want us to find the area under the curve of the function they actually gave us, but we'll address that in a minute. So first thing, recover the function. So they want us to do the derivative of this. Before we do that, we got to bring our dx over. 2 sine squared x over cos cubed x plus 1 over cos x. Okay, so there's a couple of formulas we're going to utilize in this one here. The first thing we're going to look at is anywhere I have sine over x, sine x over cos x, I can call that tan x. The second formula I'm going to use is for sec squared x. Let's pop that formula out. So if I had sec squared x, I could write that as 1 plus tan squared x. And there's a third formula as well, which I use for this. But I just you need to just let me know if you've done this formula or not. And it has to do with integrating tan squareds and tan cubes and cos cubes and sec squareds and things like that. That you might have done these formulas which already. But it's basically called the reduction formula. It's a formula you use basically just to speed things along when you're doing trig ratios of powers. So if in this particular one I'm going to need it for sec, and I'll have a sec cubed x at the end of this, but sec to any power of x dx is a specific derivative every single time. So it's sine of x times sec of whatever your power was, m minus 1 of x, all over m, remember m stands for your power, minus 1, and plus m minus 2 over m minus 1 times the integral of sec minus 2 plus m of x. Now remember again, m was whatever power you were integrating, dx. Okay, and that's what those will be using these formulas to solve this integral. Okay, so first thing here is we've got our sine squared x over cos squared x. So we're going to rewrite that. So sine squared x over cos cubed x. Well, I can rewrite that as sine squared x over cos squared x times cos x. So all I did was break my cos cubed into cos squared by cos. But I've got a sine squared x over cos squared x, and that's equal to tan of x, tan squared of x, over cos x. Now, if I've got a cos x underneath the line, another formula can tell me that if I have sec of x, that's the same as 1 over cos of x. So another formula from our tables. So here I have 1 over cos of x. That can be exchanged for a sec of x. So it'll be tan squared x times sec of x. Okay, we're still not even finished with that, because now we can manipulate this formula here. I've got sec squared equals 1 plus tan squared x. So if I want the tan squared x on its own, I'll bring my 1 over to become minus 1. So I could write that as sec squared x minus 1. So now I'm going to rewrite it again. So my tan squared x is now sec squared x minus 1. And that's being multiplied by sec x. And then finally I'll multiply that in. Sec x by sec squared x is sec cubed x. And sec x by minus 1 is minus sec of x. So I can do a lot of exchanging there. I'm also going to utilize this one more time. So everything that I have there in the first section can be sec cubed x minus sec x. So dy is equal to sec cubed x. Now I've got my 2 in front there, sorry, 2 sec cubed x minus sec of x, plus, now as I said, 1 over cos x can also be written as sec x. Okay, and I've got my dx there at the end. So I'm going to fiddle about with that again. So dy is equal to 2 sec cubed x minus 2 sec x, and then plus sec x. So minus 2 sec x plus sec x would just be minus 1 sec x. So I have 2 sec cubed x, sorry, sec cubed x minus sec of x. So that's what I'm going to try and integrate. Okay, so we're going to integrate those separately. So I'm going to integrate the left, so that means the right. So when I integrate the left, that's just y. And I'm going to bring 2 outside here. Now I'm going to be integrating the sec cubed of x, but I'm also going to be integrating the minus sec of x here. So all I'm going to do in that case is I'm just going to write it as a separate integral. You don't have to, but it just makes things a little easier to look at. And I'll throw the dx after both of them, or you can put brackets around everything and put dx at the end. It doesn't really matter. Now, so this is a killer of an integral here, and essentially it's done by substitution, but it's a long process. So we use a reduction formula. So it's 2 times. So I'm going to do my sec cubed x first. So let's have a look up here at our reduction formula. So I've got sec m. Now in this case it's sec cubed x, so my m now is 3 here. So that would be sine x, okay, grand job, sec m minus 1. So m was 3, so m minus 1 is 2 of x. All over m minus 1. m was 3, so 3 minus 1 is 2. Plus m minus 2, so 3 minus 2 is 1. m minus 1, 3 minus 1 is 2. Now, I have the integral then of sec of minus 2 plus m. So minus 2 plus m. Minus 2 plus 3. Minus 2 plus 3 is 1. So sec to the power of 1x, or just sec x, which is nice, dx. So integrating sec cubed of x turns into this expression here. That's called my reduction formula. You've one for tan and cos and sine and all of that as well. So sine x by sec squared x, sine x by sec squared x, all over, I think it was 2, wasn't it? All over 2 plus a half times the integral of sec x, plus a half times the integral of sec x, and then I still have, dx there now, and then I still have this part minus the integral of sec x. Now that's slightly different there because it's not being multiplied by 2. Yes, sec of x dx. Okay, so multiplying in there, so I've got 2 times sine of x sec squared of x over 2. Then I have 2 times a half, which is just 1. So I have 1 times the integral of sec x, then outside dx, and then outside I have minus the integral of sec x dx. Okay, now it's handy here. I have sec x dx minus sec x dx. They're gone. They cancel each other out. And my 2's here, gone as well. So y is equal to sine x times sec squared x, which is absolutely fine. But of course, just to make it look like hers, we also know that sec x can be written as 1 over cos x. So that way I could write sec squared x as 1 over cos squared x. So what I've got then is y is equal to sine x times 1 over cos squared x, which is just y is equal to sine x over cos squared x. And don't forget then, plus c. Okay, now I've got my plus c there, and that's what I want to figure out. So let's have a look. They give me the x value, y of 1, that means that's the 1 is the x value, and that's the y value. So I plot those in, and I'll find what I need to find. So what have I got here? Y is 2.82 and x is 1. So 2.82 sine of 1 over cos squared of 1 plus c. We'll work that out there now. Okay, so I'm check a number there. It's supposed to be, oops, yeah, sorry, I put in the wrong number for y, 2.882. That would have thrown me off. 2.882. Okay, so I got 2.882. Now remember, we're working in radians. Sine of 1 over cos squared of 1 in radians will also give me 2.882 plus c. So when I bring that over, it becomes minus. So 2.882 minus 2.882 is 0. So c is 0, but basically there's no c. So my derivative, my integral is just this chap here. And then after that, all we got to do is find our integral, or find our area under the line. So our integral is sine x over cos squared x. We have no c, and then we just need our limits. So we'll just check our limits here. Our limits for this question are minus pi over 3 and pi over 3. Brilliant. Okay. So minus pi over 3 and pi over 3. So plug those in. So sine of pi over 3 over cos squared of pi over 3. Be careful putting that into your calculator. Put it as cos pi over 3 all to be squared with brackets around it basically. And minus the sine of negative pi over 3 over cos squared of negative pi over 3. Okay, when we calculate that, so you get 6.9282. So the integration, put in my limits, that's my area under my curve, and that's units squared.